Hey everybody, this is Larry. This is me over Q4 of the bi-weekly contest 139, Cave Smallest Paths XOR Sum. Hit the like button, subscribe button, join me in Discord. Let me know what you think about this one. Okay, so this one is a couple of things. I think the thing that I would mention is that there's a lot of setup, but they don't really do anything. They're like what I would say the easy part of the problem, right? The part of the problem that doesn't really do anything. And what I mean by that is just like path XOR sum, right? All it does is say, all it means is that there's a lot of reading here, right? But all that means is that for a subtree, we just have n values, right? So a subtree of size k, there's k distinct value. Well, I guess they don't have to be distinct, but just k values, and you have to find k is a terrible variable because k is also one of the inputs. But yeah, right? You have a subtree. You have like x value number of values. You have to find the k distinct smallest one. That's it, right? I mean, the XOR sum part I'm not gonna go over in detail because that is just by itself. That is just a depth first search or breadth first search. You know, you can do it in any number of ways. It's just like almost like a shortest distance kind of thing, right? Yeah, shortest path. So I'm not gonna go over that too much. I think the first thing that I noticed for this problem is, well, that was the first thing. The second is actually a little bit critical, and this is something that I don't know if you could get it if you haven't done it before. And maybe I mean, I wouldn't say that it's impossible to get. You may YOLO it and get it just by luck, honestly. But it is something called smallest into large, right? And the idea here is that when you're merging two things, especially when it comes to a tree and something recursive, you always go from the smallest to large. And you may ask, well, how does that help? Well, the help part is that the complexity just works out. Okay, so I think the worst case is actually a binary tree, right? For what I'm about to show you. Let's say you have a full binary tree, right? And we'll show a couple of examples because I think this is the first time I've seen it on Leetcode. I mean, maybe other problems used the idea, but maybe not necessarily, meaning that there are other ways to solve it. Maybe there are other ways to solve this one too, but this one was the first thing that came to my mind. Let's say you have this, right? And you know, maybe they go down further, right? And the idea here is that, okay, let's say this subtree has 10 elements, this has 10 elements, so then this has 20, 40, and 80, right? Maybe I should change the colors. Okay, whatever. Because now this looks like 400. But in any case, right? And then the idea here is that, well, how much, you know, to get the full complexity of this, of all the merging, what is the complexity, right? Well, for each element, if you just look at one element here, say, and then now it gets merged into this one, right? But what does that mean? That means that half the elements do not get moved. That's why it has to be small going into large, not a generic merge where you have to reallocate space, right? And that's actually a key part of it, because then now, not all the elements move, but it only moves if it's in the smallest part, right? And if it's in the smallest part, then that means that it only merges at most log n times, because how many times can a cell be at the smallest part, right? Well, in the case that this is equal, this is the worst case, because then now you basically merge every time, and if you merge every time, then now that cell, that node, that value only has to go in log n steps, right? So that's kind of an idea. I mean, it's not a strict proof. I think you should, if you have more questions about it, I think you should definitely Google this. It definitely is an idea. And so this is kind of the worst case, but to contrast with. And what I mean by that is that let's say you have another case of a linked list, right? And this is why you actually need the small to the large and not just create a new set. It's because, okay, let's say you have a linked list-ish, and then you go dot, 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 right? Maybe not a, I mean, a linked list works too, but maybe just here where, you know, it merges with one node, maybe that's a little bit easier to visualize as well. So here on the left, dot, 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 this dot, dot, dot has 900 elements, right? But here on the right has one element. Well, what happens is that then now when you merge them, what do you do? Well, it's just one operation, right? You merge the 1 into the 900 and now you have 901. And then now you merge the 1 here, you have 902, but only one operation as well. So you don't create a new object, just to be clear, right? 903, one up, right? And all the way up. And that's it. That's the idea, because for this case, if you create a new object, in the log n case, maybe it doesn't matter that much. I think it's still, I mean, it's still not great, but it doesn't matter super much. But in this case, if you reallocate a new space for each node, then what happens? Well, this means that this did actually 901 operation, right? Because you have one, so you have to create a new one by copying over the 900 elements by, well, taking 900 operations plus one more for add, and then 902, and then 903, 904, dot, dot, dot. And you know, you dot, dot, dot back out, it's gonna be 1 plus 2 plus 3 plus is equal to n squared, right? And that's, and you want to avoid n squared for obvious reasons. And that is, it's not a proof of the smallest to largest, but this is the visualization that we'll go with. And of course, like I said, you can certainly feel free to Google it to kind of have a deeper understanding of it. But that's how I would use it as a thing. So then now, after so with that idea, the next thing I was asking is that, okay, we do it this way. The thing about this is that it's destructive, right? The merge operation, because like we said, we're not allocating space again, we're merging. So that means that you kind of in a way destroy the original object on the bigger side, or even the smaller side, you just kind of throw away maybe, but right? So then how can we do to solve these queries? I think for me, right after that, I was like, oh, well, now we have these nodes, and let's say we are able to get the answer for the nodes very quickly. You have X number of them, and you're trying to get the kth one. Okay, fine. Honestly, at that point, I was a little bit messy, but I was like, okay, then how do I figure out the queries? Because we just do them in order, right? And then the next observation is that queries, you know, they give it to you in that way, do not have to be live. They do not have to be answered in the order that they're given you, right? So the idea is just pre-processing it, and that's it. Why is my code not here? Leetcode does this thing with contests. Okay, I don't know. It's a little bit awkward. Anyway, yeah. So the short answer there is that pre-processing the queries such that you have the query, this is the actual query, and then the index so that you can later do it on. And that's basically it. This is actually a relatively short solution. I want to say 43 lines, and we'll go over it. So first we set up the tree, right? We have a rooted tree at 0. We just set it up. This is nothing too fancy. We set up to be top down so that we could do a recursion down, right? This is what's it called? Fundamental graph? No, functional graph. Sorry, yeah, functional graph. So we kind of set it up that way. You don't need to know that. We set up the answer like this so that we are able to kind of fill in the answer as soon as we know the answer. And then we kick it off by calculating, starting at the root node 0, and current is just the current XOR path sum, right? Or whatever, that made it around. You return the answer afterwards. And this is it, that's the recursion. Is that we have the current node and then the current XOR, right? So node, current node. And here we update it by using the XOR with the values of the node. I use the sorted set because we need a set to get rid of the dupes. And that's basically it. I have the set, I start with a set. And then for each child, All the illustrations that we did was with binary trees, but it's actually even more illustrative with more children, because then now instead of branching out per two, the smaller one gets smaller, right? Like a lot. So like very quickly. But yeah, so then now, yeah, for each child, we calculate the result set for the child. We have an R, and that's all it is. From if it's larger than the smaller one, then we take the smaller one, we merge the larger, and then we just update S because that's our current set. Otherwise, we update it this way. And this is actually a key thing to notice, is that this does not actually create new objects. It's a merge in place. So we don't create a new sorted set. And it's very easy to kind of like just write it like this, and it is a whole world of different, because that does create a new object. Yeah, that's basically the thing. And so, and in Python anyway, what this or Leetcode does for a set, it just does I actually don't know implementation detail, but other than the fact that it does not create a new object, that was the key part for me. And yeah, it takes every element and put it into R, and then here it just updates R so that now S contains it, so that for the next element in the loop, S contains all the elements, and that's it. And then after it processes all the children node, it enters the query. So if there are any queries on this node, that's it. We get, and keeping in mind that with sorted set being important and is sorted, so I guess they're both important, the sorted part and the set part, you're able to get the k-1 number very quickly. Otherwise, return -1, and that's it. Very short code, and that's how I was able to get this in about 13 minutes, 12 and a half minutes, pretty quick. Honestly, compared to my Q1 and Q2, this was done pretty quickly. And the key part of it is just knowing this small to large thing, which I don't know. I was gonna say, do you need to know this? I don't know. I didn't need to know this when I was starting up in competitive, but I don't know too well anymore. But yeah, so what's the complexity, right? Well, it's easier to do the amortization for per node, right? So per node, per cell, just a small to large thing. So I think the biggest thing is going to be this part where you merge elements together, because this is just all of one per query, easy lookup, right? Or actually, I lied. This is log n for getting the k-1 smallest element. So okay, so maybe q log n. Yeah, q log n is for this part, but here it is going to be n log n for all the merge sort. So you could say that in total, this is going to be all of q log n plus n log n, right? And that's it. That's all I have with this one. Let me show you the top. This is the setup. Like I said, this is to set up the tree, set up the queries. Yep. Set up the answer. Set up the whatchamacallit, the recursion with the small to large, and then kick it off and return the answer. And that's it. That's all I have. Thanks for watching. And you can watch me solve a live in contest now. Okay, hardest problem. How much time do we have left? An hour. We should be able to do a hard problem in an hour. Alright, cave smallest path XOR sum. Each node I have. Okay, let me reread this. I'm like not focused. Alright, Larry, focus. Alright. Okay, you have an undirected tree at 0, okay. Okay, so it has parents and no thing, okay. The path XOR, big XOR, XOR, okay. Find the cave smallest distinct path, what? Inclusive, okay, you're given 2D away. The cave smallest. Okay, I mean, I guess so. Okay, I think I understand it, but I don't know how I would even think about it. What is there any, look at the constraints, k could be big. Is there anything small that we can abuse? Doesn't seem like it. Right, let's set up the tree first. Of p dot append I, right? Now we have the tree. We could do a XOR calculation. Path XOR sum. What is the path XOR from root and the node? Oh wait, I think I misread this one. Understood this one actually. I thought it's from any two nodes. Oh no. From the root to a node U. I don't think I understand this one. Or like, I don't think this is that hard, is what I mean. Maybe I misread it the first time. But I don't. Of course, if you do it naively in a linked list thing, it'll be too much. So then it is like it's whatchamacallit. I mean, there's like a binary search component, I guess, but maybe. Right. And also, we don't have to do the queries live. Can I do the queries in another way? I think that's the way to go. You don't do the queries live. Okay, yeah, I think that makes sense. Okay, yeah, I think that makes sense. Yeah, okay, that makes sense. And then it's just small into large, and then that's it, right? Small into large queries not live, right? So then now we do for UK in queries. Then now, yeah, maybe oops. What am I doing? Why am I writing? What is the deck? I think I just write Q and then I naturally write deck. That's not what I want to write. Yeah. Yeah. Oh man, reflexes. So something like that, right? And Q for queries, not just a regular Q. That maybe is confusing. Okay, let's just use QS. Maybe that's slightly better. Okay, so then now. Yeah, okay. Right. Something like that. None times Q. Let me just go Q. I don't think n matters, but I you know, I just like writing out. Okay, so then now XOR XOR sum. Okay, from the root though, not from. It is subtree, but okay. So then now this is the current, and you have to keep track of current, right? Okay, yeah. So then now. Node. Okay, so we. we do a set, but we want to small into large, right? So then now for I don't know, naming things is hard. Child. R is equal to, okay, so then here we set a set of code. R is equal to calc C current. That's fine. And then now if length of R is greater than length of S, then yeah, then R dot, I think add S maybe. I don't know if that's the notation actually. I think here's, but then S is equal to R. Okay, and then yeah, and then now we do the math, which is the queries. So yeah, for if length of QS of node is greater than 0, then is it fast enough if we do it so? Do we need to do a binary search? Binary search is just going to be slow though, right? No, you do 1 bit at a time. Now then you have to go through the list, so you might as well search. What am I looking for again? Oh, the cave smallest. I mean, okay. Actually, I didn't think this part through. But at the end we return S. I'm trying to think whether I should use a different data structure. I think so, maybe. Yeah, okay, fine. I mean, this is also not that fast. That's why I'm not that's why I'm not like, yeah, that's why it's not immediate. Let's see, I got sorted set, merge to set. I want to know if this is easier syntax than writing out the for loop. Union, or okay, so they create a new set though. That's what I don't want to do. Okay, this does do the in place union. So I guess actually I don't have to change that much more code, because then now we can write answer of index is equal to S of K. Is K 0 indexed? First, it is, so then -1, but also if length of S is less than K. This is so awkward. Where's my thing? Okay, whatever. K is 2, even if it's equal to, right? No. I'm so bad at indexing. Whatever. Okay, so I'm writing it the other way, but okay. Alright. Why did I write things so awkwardly? What did I click on? No. Inspector. Alright. That's fine. How? Oh, it's not linked to Q. A lot of silly mistakes. That's QS sub node. Okay. But is it fast enough? That's the question. YOLO. Okay. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem, today's contest, everything in between. Stay good, stay healthy to your mental health. I'll see y'all later and take care. Bye bye.